Okay, for those of you who missed the lab, amino acids, week 15 lab, I'm going to go over this and give you some ideas as to how to complete this lab. Let's first look at the structure of an amino acid. So the amino acid has this basic structure. It has an amino end and a carboxylic acid end, and it contains an R group. The R group is what determines the kind of amino acid we're dealing with. So this is essentially a neutral structure of an amino acid. So you're going to answer the pre-lab questions, and then you're going to go to section A and complete this information. So the first thing you have to do is draw the structure of glycine. I'm going to do this for you, but I want you to draw this as a neutral structure. Neutral structure. So I'll do it for glycine. Then you do it for alanine and serine. So again, as a neutral structure, the glycine contains an amino terminal and a carboxylate terminal and an R group. In the case of glycine, it's H. So that's a neutral structure of glycine, and you can do that for alanine and serine. Now, in terms of the zwitterion structure of glycine, which occurs at a neutral pH, you have to draw the amino as a charged particle. So that's going to be NH3 plus CH and COO minus, and the R group is still H. So this is the zwitterion structure. You're going to draw glycine as a structure that occurs in base, which means you're going to pick off one of these hydrogen ions and redraw it. And then you're going to draw it as glycine and acid, which means you're going to take this zwitterion and add a hydrogen, and this becomes 1 plus. So you draw that in these boxes. Okay, let's move to part B of the procedure. What you see here in this diagram and this figure is what you were supposed to do. That is to say, you were going to take some paper and you were going to lay it out, draw a line at the bottom, and spot it with the 7 amino acids to be analyzed. At that point, you were going to put it into this chamber, which contains the mobile phase, a solvent consisting of isopropanol and ammonium hydroxide. The solvent, the mobile phase, was then going to creep up the paper and take with it the amino acids that were spotted. And depending on the hydrophobicity of the amino acid, it was either going to travel far or travel small. So unfortunately, we have none of this equipment. So we're going to essentially do this as a virtual exercise and predict the migration of each amino acid based on its hydrophobicity. So these are the 7 amino acids we're going to plot. We're going to spot phenylalanine, alanine, glutamate, serine, lysine, aspartic acid, and an unknown. Now, I have drawn these structures at pH 7, which consists of their zwitterion. So, in terms of the zwitterion, the bottom part of the amino acid for all of these amino acids is going to be the same. So we can essentially ignore that and consider only the R group. Nevertheless, I've redrawn these amino acid structures at a pH of 10.0, which essentially is going to be the pH of the solvent that we're using as the mobile phase, because it's going to be in ammonium hydroxide, which is base. So these protons, one of these protons is going to be pulled off, and we get a neutral amino structure, but we still have a carboxylate that is a charged carboxylic acid structure. So in terms of predicting what the hydrophobicity of the R groups are, we're simply going to consider the R group alone. The bottom part is always going to be the same for each one of these amino acids, so it's not going to play a role in the relative migration of each of these amino acids. So the way we're going to do this is that each R group is going to contain a carbon, oxygen, nitrogen, or a carboxylate group. And we're going to assign a polarity factor to each one of these R groups, a scaling factor. So this is going to be a hydrophobic scaling factor. That is to say, if the R group contains a carbon, that's going to be a positive hydrophobic scaling factor. That means the R group is going to cause the amino acid to travel far. If it's these polar groups, an oxygen, nitrogen, carboxylate, they're going to have scaling factors of, for oxygen, -1, nitrogen -1, carboxylate -3. And these negative scaling factors are going to cause the amino acid to move slowly. So we're then going to fill out this table and add all of these up. So in terms of the scaling factor, each amino acid is going to start with a 5. So each amino acid gets a 5. But then we're going to count the number of carbons, oxygens, nitrogens, or carboxylates and fill in the table. So let's start with phenylalanine. The R group of phenylalanine has 1, 2, 3, 4, 5, 6, 7 carbons, no oxygens, no nitrogens, no carboxylates. So in this table, carbon has assigned a value of 1 times 7 because there are 7 carbons, so it gets a value of 7. No oxygens, that's blank. Nitrogens, blank. Carboxylates, blank. So the total is going to be 12. 12 is going to be the largest total we have of all the amino acids. So this amino acid is going to travel far up the page. Now, let's do another one, aspartate. Here is aspartic acid, and again we consider only the R group, which is in this area here. There's 1 carbon and 1 carboxylate. So when we go to our table for aspartate, again all of these start with a 5. It's got 1 carbon, so that's +1. It has no oxygen, has no nitrogen, but it has a carboxylate, so that gets a -3. We add all these up, and that's going to be 6 minus 3, or a total of 3. So this is the smallest scaling factor that we're going to have as a total. So this is not going to travel very far at all on our paper. So I've sent you this information to explain how to fill out the group, the B1 chart. So anyway, this is kind of an expanded version of the B1 chart. So it's essentially a rectangle. You're going to draw in the starting line, and you're going to add these 7 amino acids: phenylalanine, alanine, glutamate, serine, lysine, aspartate, and the unknown. And then on this side, you're going to scale it with the hydrophobic scale. So near the top, you're going to have 12. You're going to bisect it and put a 6. You're going to bisect it again and put a 4, and bisect it again and put an 8. And that's going to be your scaling factor. And then you're going to plot the information. So for phenylalanine, it's going to be 12. The total scaling factor is 12. So you go up here and you put a little spot where 12 is. And for aspartate, it's going to be 3. So you look at the scale, and we're going to go up to where 3 would be, and then we're going to put a little spot. Okay, and then you'll do that for the other 5 amino acids. So you're going to essentially do that on this sheet of paper. So you're going to start the bottom, the start line, and you're going to put in a stop line. And you're going to measure that, that distance in millimeters. So, for example, if I measure that, that's roughly going to be 4.8. So I write that right here, 4.8. And then for phenylalanine, which moved almost to the top, you're going to measure that. And in this case, that's going to be about 4.3. So right here, you write 4.3. This color box, we're going to X out. And we're going to calculate the RF factor, which is going to be 4.3 divided by 4.8. We're going to calculate this value. So that's 4.3 divided by 4.8 equals, this is going to be 0.90. And you do that for all of these, even the unknown. Now, the unknown has a value of 6. And it turns out when you calculate it for serine, you're going to have a value of 5. So the unknown is 1 more than serine. So you have to look at all of the structures that are available, all of the amino acid structures that I will provide for you, and you are going to determine what amino acid looks very much like serine but has 1 more carbon. And that's going to be your unknown. And you're going to put it in here and explain why. You're going to say, the unknown is XYZ because it has a value that's 1 greater than serine. So you're going to find an amino acid that's very much like serine, but it has an additional carbon. So then you're done with part B. Answer all of the questions and turn in your lab as designated on the syllabus. And there we go. Thank you.